Hello and welcome to the course Design Bore Fields with Confidence. In this third and final chapter, before the answers of part 4, we will look at the hydraulic design of bore fields. Now, the last two chapters we talked about the pressure drop and how the pressure drop changes over time. We introduced concepts like pump energy consumption and pump power, and now we're finally getting there. We're going to look at the hydraulic connections between the boreholes to the manifold, and also make it more practical. And we will show you how you can use GHEtool to actually calculate the whole pressure drop of your hydraulic network, your geothermal bore field. Now, to start, we have 4 different types of hydraulic connections: direct connections, parallel connection, Tickelman connection, and series connections. Now, in the case of a direct connection, this means that we have a manifold somewhere. And for bigger bore fields, it's perhaps a manifold chamber outside of the building or at the edge of the cellar. For smaller projects where there's just 1 or 2 probes, perhaps they're connected in Tickelman, we will discuss later, and there is no real manifold. But anyhow, conceptually, a direct connection means that you go from your borehole with one individual horizontal connection to a manifold or to the heat pump or whatever. Now, the main advantage of this is that the flow of your borehole is equal to the flow of your horizontal network. It's very flexible. You have quite a lot of control since all the boreholes are connected individually. You can control each of them, the flow in each of them. It's also rather safe because if something goes wrong with one of the boreholes, you can simply disconnect one of them without losing a bunch. So there are a couple of advantages of this direct connection. The downside is it's rather expensive. It is to say you need more horizontal meters. If you have 100 boreholes and you need to connect each of them individually, well, you have quite a lot of pipes running back and forth. So that has an added cost. On the other hand, you also need a bigger manifold. If you need a manifold chamber with 50 connections or with 100 connections, it will be a bigger manifold. And if it's installed under the ground, the manifold chamber should also be bigger, etc., etc. So the cost is higher for this type of systems. And it's also harder to achieve turbulence. Now, that's the case actually for the coming 2 options as well. And that's because, well, since every borehole is connected individually, this means that our flow is divided by the number of boreholes, giving you, let's say, the lowest of potential flow rates. And if you're working with W tubes, for example, it can be harder to achieve turbulence, as we will see later in this chapter. So that's a little bit the direct connection, or the direct coupling. Another option is to work with parallel connections. Now here we have 2 different options, and the one on the right, so-called direct return piping, it's called, in this case, the parallel connection. The other one we will discuss in a second. And the idea here is that we are going to group boreholes, groups of 2 or 3, together, and that we're going to connect them with one horizontal connection to the manifold. So this means that the flow through a horizontal connection, it's actually the flow through each borehole multiplied by the number of boreholes in one particular group. So as with the direct connection, the flow rate through each borehole still remains the same, but it's now the pressure drop, the flow in the horizontal connection, that will increase. Now, of course, the positive side of these parallel connections of bore fields is, well, it's cheaper because, you don't need as many horizontal pipes. Your manifold chamber, your manifold itself can be smaller, which is all advantageous for an investment point of view. The problem is that there is not a lot of safety. Imagine one borehole fails. There is only one connection to the manifold, so you immediately lose all the boreholes, or the whole group of boreholes in your bore field. So that's a little bit a risk there. And another risk, or another problem, is that there is no equal flow. And you can see that actually on this schematic to the right. You see the flow comes from the pump, and it can choose between borehole 1 or borehole 2. But since the hydraulic route going through borehole 1 is actually shorter, and there is less pipe, you go into one and you immediately go back. This also means that there will be less friction, and it will be easier for the flow to pass through that. So the boreholes do not have equal flow, and as we will see in a second, this is actually what we want. So that's also why you do not have the option to work with parallel probes or parallel hydraulic in GHEtool. But what you can actually do is to go to the left option and go for a Tickelman connection. Now this is also called a reverse return connection, reverse return piping. And the idea is here the same. We group the boreholes in number of n boreholes. And what we do is, instead of going from borehole 1 immediately back to the manifold, we go further to borehole 2 and then go back. And this has the added advantage that the hydraulic length of each, no matter the borehole the fluid chooses, the length will always be the same. So the pressure drop is also the same, and hence will your flow rate be. So for this Tickelman connection, which is then very often used in geothermal bore field design and in the whole of HVAC engineering, let's say, our flow in the horizontal pipe is still the same. It's the number of boreholes in each group multiplied by the flow through each borehole. It's again cheaper. It's a little bit more expensive than the parallel connection because we need some more piping, but it's cheaper than the direct connection. Theoretically, we have an equal flow rates because the pressures are equal, and the only difference in flow rate one can expect is due to irregularities in when it's actually installed. But theoretically, it works extremely well. But we have again here the issue with safety. If one borehole fails, we lose the whole group, so there is a risk involved there. And the last option besides direct connection, parallel connection, and Tickelman connection is actually connecting the boreholes in series. And this you see here. And what this means simply is you come from your manifold with a pipe, you go into your first borehole, out, and again into the next. And this you do for a number of boreholes, typically 2 or 3, and then you go back. So again, here we're grouping the boreholes in groups of n, right? And the number of boreholes. And here the flow of our horizontal system is actually equal to the flow of our borehole itself. It's a cheaper connection, again, because of less horizontal piping. But the main advantage of series connection is that you have a higher flow rate. Now, in comparison to Tickelman or direct connection, your entire flow to the bore field is not divided equally across boreholes. But here you can actually work with these groups. So the flow rate through each borehole is actually higher, making it easier to get turbulence and potentially enhancing your hydraulic and your thermal design. The problem here again is safety. And we again have one group, so if one borehole fails, we need to cut off the whole group. And there is another problem related to practicalities, and that's the problem of air. Now, when you're connecting these boreholes together in the fields, we need to vent them. There is always some air bubbles inside of them. And typically what you do is you place a pump and you pump through it in order to get all the air out. But if you connect deep boreholes in series, the air gets trapped in the high parts between the boreholes. Because you have to imagine if your borehole is 100 meters deep and you have some air pockets in between those boreholes, you need to get this air 100 meters down in order to get it out of your system. And that sometimes can be hard. So one way to do this is to place vents on the higher connections to actually get the air out as much as possible before actually closing up your system. But on the other hand, also just pumping real long and with a very, very high flow rate to get the air out of it. But that's something to be aware of. So these were the 4 different types of horizontal connections. In the textbook, we also discussed that you can combine each of them. So you can work with groups in Tickelman, connected in series and so forth. But typically, I would discourage that because there's a risk of making mistakes in practice in the field. You have to remember, in the field there are just a lot of mud, pipes coming out of the ground. It's all black and it's really easy to make mistakes. So I'm sure and I'm aware that for some design reasons, it could be interesting to combine series and parallel connections and so forth. But for practical reasons, it's discouraged to do so in order to limit the amount of risk for mistakes. Now, this was everything I wanted to say about the horizontal connections. And so far we have talked quite a lot about the pressure drop for each of the boreholes, and yeah, we can calculate that. We have the length, we have the local losses and so forth. But the question is, well, these are the losses of the bore fields, of the borehole better. Every borehole has a different horizontal length, and there are different bends and so forth. And the question is, how do we go from the pressure drop for each borehole, which you can calculate quite easily, to the pressure drop of the entire bore field? And this is done with the concept of hydraulic balancing. Now, what does this mean? It's to say that we want an equal flow through each of the boreholes. And we already mentioned it when we're talking about parallel versus Tickelman connections. We want this equal flow. And the reason we want this is because if we have an equal flow through each borehole has the same contribution to the energy exchange with the ground. Later we will see that that's not 100% the case, but conceptually, if we give them the same flow rate, they can have the same contribution to the thermal behavior of the system. And the way to do that is to make sure that the fluids has all the options to go through, let's say. So if we make sure that every borehole has the same pressure, equal pressure, we can ensure that they will have the same flow rate. And the way we do that is by these balancing valves, or these flow regulators. We place them on the manifolds and we can just turn them and make sure that the flow rate in all of our boreholes is actually the same of all our connections. So the only thing we need to care about is basically our worst case pressure drop. Because if we find the furthest borehole, the one with the highest friction losses, we know that all the other connections to the manifold, we need to turn these balancing valves such that they will have an equal pressure drop to the one that's the furthest away. So basically, the goal is find the worst case, find the longest horizontal path, we calculate that pressure drop, and that in the end will be the pressure drop of your entire system. Now, let us take now a look at an exercise in GHEtool. So I have here a building with 12 boreholes to the sides. We have a manifold in the building itself. So there is no horizontal connection from the manifold to the technic room itself. It's already there. And we know that our furthest borehole is actually the one in the top, in the bottom left. And that's, if I'm not mistaken, 6 plus 6 plus 6 plus 6 plus 6, 12 plus 18 meters. It's 30 meters of flow, of pipe. So in a second in GHEtool, we know that the horizontal connection, the lateral pipes will be 30 meters. And let us just also take into account the minor losses. So over on the textbook, we have a table with all the minor losses, but now let us just assume that every bend junction is the same. It's 0.5 as a K value. Then we know that we start in the manifold with these control valve. Let's assume it's also 0.5 there. Then we go to our bend. That's 1 in the end. We pass, or we go right to the bottom. That's another half. So we have 3. And that we basically have, it's 1.5, and we have that 2 times. So it's 3 in the end. Now let us jump into GHEtool and show you how you can fill in and play around with it and basically show you how you can make hydraulic designs in GHEtool Cloud. So here we are in GHEtool Cloud, and I created a new project for you based on what we saw earlier, the bore field with these 12 boreholes. 12 boreholes of 120 meters deep. Now again, if you want to follow along, the report of what we're going to do is again in the textbook, and you can recreate these scenarios yourself. So let us go down and scroll to the hydraulic design section. I say, yes, we want to calculate the pressure drop in the bore field. Now we're going to start with Tickelman and series connection set to 1, which means that basically as a reference scenario, we are going to connect all the boreholes directly to the manifold. So we have a manifold with 12 connections. We're not going to include a header pipe because we said the manifold is already in the technical room. So perhaps we could say, well, it's 1 or 2 meters, but in the end it will not play that big of a role. So let's ignore it for this case. And we said that the longest horizontal path, it was 80 meters horizontally, 12 meters down. It's actually 30 meters in total. Now, what is important here is that we have 30 meters in one direction, 30 meters back, but you only need to enter it once because it's automatically doubled in GHEtool. So it's the distance and not the entire length of the hydraulic path. And then here we see that we have a K value for the lateral pipe. So basically this was all the bends the pipe went through, and we calculated it and it was 3, namely the manifold valve, then one right angle bend, and then one bend at the end to go down the borehole. And that we have 2 times multiplied by 0.45, so it's the K value of 3 in the end. So let us go ahead and calculate this. Perhaps also interesting to know, because we're going to change it later on, is that this is going to be with a W tube, DN32, monopropylene glycol, and we work with a constant temperature difference. So we actually update the flow rate in heating and cooling separately. Now for the thermal demand, it's 37 kilowatts of heating and only 4 of cooling, so it's way more heating. You also see that in the yearly energy demand, 67, when compared to even less than 3 megawatt hours per year of cooling. So let's go to the results, and you clearly see here a negative imbalance going down to 0 degrees after 50 years. And then we have here our hydraulic design. So this is the graph we talked about earlier, showing you the pressure drop and also the pump power in extraction and injection, because we have different temperatures. We also see different pressure drops and pump powers in heating and cooling. And what you can see here is we have a higher flow rate during heating. And of course, we have 37 kilowatts here. And for cooling, we only have 0.35 liters per second. You only have a very low power in cooling, giving us this lower flow rate. And let me take away these pump powers for the moment. You clearly see here the jump from laminar to turbulent. Now for extraction, this happens at 0.4 liters per second, because as you can see here, we're extremely laminar. And for injection, it's even more laminar due to the simple reason that, our flow rate is incredibly small. So, but now if we look at the pressure drop, we see here we have a pressure drop across one borehole of 13 kPa, and the horizontal part is only less than 3. So in total, we have 16 kPa needing just short of 60 watts electrical power to make sure that this system works. And we have an estimated pump energy consumption of 75 kilowatt hours per year of electricity. Now, let us go ahead and change the hydraulic design shell. So we're going to call this scenario 2, Tickelman connection. So instead of connecting all the boreholes directly to the manifold, we're going to say, let's group them in groups of 2. And let us calculate now the scenario again. So what we would expect, because we know that Tickelman just equally divides the flow, is that the pressure drop inside the borehole stays the same, but our horizontal connection now gets way more flow rates. And if we scroll down, that's exactly what you see. So I have here the same 13.21 kPa as before, but our horizontal pressure drop is now almost 5 times bigger because we now have a way higher flow rate through this horizontal connection. So this also gives us a higher pump power and also 30 kilowatt hours per year of extra electricity needed to keep the pump running. So that's for the Tickelman connection. Now we can do the same for a series connection. Now, let me go ahead and type that for you, series connection. And to do that, we go to General, and we simply say, well, let's connect them not in Tickelman, but let's connect them in series. Let's go ahead and run this. And what this will do is it will actually change the flow rate for each borehole, which we discussed earlier. So now, you already see it here, a very higher Reynolds number, still laminar though. But you see that the pressure drop across one borehole, it's almost double the one we had before, because now the flow rate is way, way higher. And the pressure drop in our horizontal system, it's the same as the one we had with the Tickelman connection, because now our flow rate is also twice as high as in the direct case. Now, if you're wondering why it's not exactly the same, that's because our temperatures are slightly different. And you know that in GHEtool, everything related to the Reynolds number and the friction factor and etc. And the viscosity, etc. It's updated in every month. So if the temperature changes, you get slight changes in pressure drop as well. So from direct to Tickelman connection, we only see that our pressure drop increases because of a difference in flow rates, but there is no thermal difference. And which you can clearly see here, there is no difference in the thermal aspects. When we go to the series connection, well, our borehole resistance changes due to a different flow rate in our borehole, and we get different temperatures, and hence this also impacts the pressure drop again. So that's now we're at almost 0.4 degrees Celsius above our zero limit. Now, this is already quite interesting. What you can also see is that, well, because they're now in series, our pump electricity consumption is almost 3 times as high, or 2.5 times as high as it was with Tickelman connection. Now let us go ahead to this Tickelman connection, or no, to this series, and instead of working with a W tube, let us say, let's work with series and single U. So what we're now going to do is let's go to the borehole resistance step. Say, okay, let's work with the DN40, a bigger probe, but now let's just use one of them. And let us run this. Now, the whole sensitivity, single, double, we will discuss it in the next part. But what you can see here is that now we're transient. And if we just, this is not the topic of the video, but look, we have here our effective resistance. When we compare it to the previous case, slightly better. Because now we have a turbulent or transient flow rate in our borehole heat exchanger, which is better due to the convective heat resistance and so forth. But also our pressure drop is now way, way higher. We're no longer laminar. We have a higher pressure drop, which you can also see here. So we're at 2.5 liters per second, which is halfway the graph, and you see that the transition to turbulence occurs just before 2 liters per second. So here, we need quite a lot more pump power, and also our estimated pump energy is at 400 kilowatts hours per year, which is also quite high. Now, of course, it's always a distinction. This single 40 probe can be more economical in practice than our double DN32. So again, their investment cost versus operational expenses, it's a trade-off, let's say. But just to put things in perspective, because here we're talking about a couple of 100 kilowatts hours per year difference. If you take a look at what the electricity consumption of the overall system is due to the heat pump, etc., yeah, it's a couple of magnitudes higher due to the fact that our heat pump is consuming way more electricity. So yeah, it's important, our hydraulic design from an energy perspective as well, but that's not going to be the final factor in your decision. Now, just to end this then, perhaps, I want to illustrate the importance of working with variable flow rates. So let's call this now constant flow. So we see here that we have basically a critical flow rate of 2.5 liters per second. It's clear that this design only cares about the extraction rate. So if you now go to our borehole resistance step and scroll down and say, well, let's work with this constant flow of, was it 2.49 liters per second through the entire bore field. Again, two connected in series. Let's calculate this. And then we will see what the estimated pump energy consumption now is. So let's scroll down. And you see here that we have way more electricity consumption. And that's mainly due because in summer, when the temperatures are higher, and we don't need that much flow rate, it's only 4 kilowatts of cooling, and we are putting an insane amount of flow through the bore field. It's just increasing the pressure drop of the overall system and increasing the pump energy consumption. So that's actually what you see here. It's 1300, let's say. It's almost 1 megawatt, or let's say 900 kilowatt hours per year more of electricity consumption when we're not using frequency controlled pumps. So this is just basically an introduction to show you how you can play around with that. In the next part, we will take a look at way more sensitivities, talking about single and W probes and thermal and hydraulic aspects combined. But go ahead, play around with it already, so you get a little bit of the feeling and you're more prepared for the questions or the topics, the sensitivities we're going to discuss in the next part. I'm looking forward to seeing you there.